right on a silver platter is what we call that. And if you missed it, it's on the video, and I will also be saying it about 7 or 8 more times before it's all over, so you'll get it. Find the Taylor polynomial. We'll do this one before the break. Find the Taylor polynomial of degree 6 for f of x equals natural log of x centered at c equals 1. All right. So this is a Taylor polynomial. Let's change that c into an a, just for consistency. That's a nice typo for somebody. And again, just to be clear, there's nothing wrong with having a C there. It's just I'm keeping it consistent with my notes. So if you see a C in a textbook, online resource, whatever, it's still saying the same thing. All right? It's some constant value. And in fact, you might say C is better than A, but I have A mostly here. So I need derivatives. So I'll start with the original function. I'll leave a little space. F prime of x is 1 over x. But since I know I have to take the derivative again, x to the negative first, leave a little space. F double prime of x is going to be negative x to the negative second. Triple prime to x to the negative third. And you know what, while I'm at it, let me just get one more in there. Fourth derivative. I wanted to actually go to the fourth derivative at least once with you, just so you can get a little refresher on the notation. It's after the third derivative, you stop using the tick marks to represent primes. So whatever the level of the derivative is, it goes in parentheses, because otherwise it could be confused with a power. Actually, if you wrote f with a power of 4 of x, that really actually does mean y to the 4th power. All right, so it would not necessarily be what you think it is. All right, so now you might look at this and say, I don't see any pattern here, but I'm looking at the coefficients, forgetting about the signs. Well, actually, maybe you don't want to forget about the signs. Positive, negative, it's alternating, so that's something to keep in mind. We also have coefficients, if you're just looking at the absolutes, 1, 1, 2, 6. 0 factorial, 1 factorial, 2 factorial, 3 factorial. Right, so it's still kind of working its way into this whole factorial business. But this time I want to center it around 1. And there's a very simple reason for why we would want to center it around 1. You know, because if you have a choice in a matter, most of the time you want to go with a Maclaurin polynomial, which is always centered around 0. But sometimes you want to go with a generic Taylor polynomial, because centering it around 0 is often, for transcendental functions, not the way to go, because, oh, well, I'll just ask you, what's the natural log of 0? Undefined, yeah. So you got a problem. Actually, you would have a problem for every one of these. So going with the ordinary, the Maclaurin polynomial where it's centered around 0 would be problematic in this case. Centering around 1 is the choice because of that first reason, but also because it's gonna give us a great degree of convenience. Because the natural log of 1 is equal to 0. F prime of 1 would be 1. F double prime of 1 is going to be negative 1. F triple prime of 1 is going to be 2, because all of those x's are going to basically cancel away. All right, so the computations, just for computational reasons, we go with the Taylor polynomial centered at 1. Right? So sometimes you decide on what you want it to be centered around just for the sake of convenience. Like, for example, if I gave you a function, let's say, I'll go back to the sine function. Sine of x minus pi. If I center it around 0, every time I replace x with a 0, I'm going to get a sign of negative pi. Not impossible to figure out, but maybe something you don't want to figure out. But if I center it around a equals pi, then every time I go to evaluate this part of the expression, the x minus a part of it, it's going to give me convenience. It's going to give me a sign of 0. Right? So when we go to tackle the derivative parts of it, you'll be finding the sine or cosine of 0 rather than negative pi. Right? So this is a nice case, but what if it were sine of x minus 11 pi over 13? Put a 0 in that, good luck in trying to find an exact value for sine, cosine, negative cosine of 11 pi over 13. So basically, you take whatever's within the trig function, set it equal to 0, and solve. That's what you should center it around. Right? Take a sign. So, the polynomial itself. Said degree 6. We learned from the last Taylor polynomial, the Maclaurin polynomial, again, which is a special form of the Taylor polynomial, that sometimes terms can cancel away. Right? So, is this enough to get me where I need to go? I don't know. Maybe I'll have to find more derivatives. I do have a discernible pattern here, so I think I'm pretty good in that if I know this is 0 factorial, then 1, 2, 3 factorial, then the next one most likely is 4 factorial. I can test it out by finding another derivative. But at least at the moment, I can get started on writing the polynomial. P sub 6 of x. So our first one was 0 plus 1 over 1 factorial times x minus 1, because it's centered at 1, to the first power. You put the little power there if you want. Right. In reality, that 0 is 0 over 0 factorial times x minus 1 to the 0th power. Because all the other stuff canceled away. All right. The next one would be plus a negative 1 over 2 factorial x minus 1 to the second power. Then we have a 2, so a 2 and a negative 6. So plus 2 over 3 factorial x minus 1 cubed plus negative 6 over 4 factorial times x minus 1 to the 4th, and so on. Now it's just a question of, do I want to rely on the pattern and keep going, or do I want to kind of stop and take stock of the situation, see what's going on? I asked the question so you know the answer. All right, so what I'm going to do is I'm going to clean this up a little bit. This is going to go to 1. Well, so then I might as well just write x minus 1. You know, I'll put the 1 in front. The next one is going to be minus 1/2 x minus 1 squared plus 3 factorial is equal to 6. 2 6 is 1/3. So honestly, I think I have it at this point, because if you look at this, the coefficients denominators seem to match the exponent in each case. If this had a denominator, it would be 1. If I wrote the exponent here, it would be 1. So I'm in pretty good shape. I think I can just kind of go for it, but let me just double check. 4 factorial is equal to what? 24. What's 6 into 24? What does that simplify down to? 1/4. So minus 1/4 x minus 1 to the 4th. So sometimes taking a sec and really thinking about what's going on can get the job done. We know it's alternating. So the next one's going to be positive 1/5 x minus 1 to the 5th. And then finally 1/6 x minus 1 to the 6th. All right. under no circumstances whatsoever should you be distributing all this stuff out. All right, hopefully that's not even something that crossed your mind to begin with. Like, you weren't thinking, well, let me just do one of these and stretch out because I know I have to distribute all this out. No, you don't. Hopefully that's not even a consideration. All right, but look for patterns because those patterns really do make a difference. And in all honesty, I mean, at the expense of stealing my own thunder a little bit, we can now get to a point where if I needed to generalize this, I think we would pretty much have it, because I would just need to come up with an expression in terms of n that would represent these two values. Okay, so if we look at this really, I'm starting off with I have a numerator of 1 in every case. My denominator and my exponent are 1 in each case. All right, so if I wanted to, and eventually I will, I could say 1 over n times x minus 1 to the nth would be an expression that could represent any term of this expansion. However, that would only give us the values themselves. It wouldn't give us the signs. All right, so all I would need to do is multiply this by -1 raised to a particular power. So if you're going through the process of thinking, okay, it's going to be a summation, right? So we're just kind of building it here. I just don't know what the power is. It's going to be a summation, if I want all of them, going from n equals 1 to infinity. We have the 1 over n. We have the x minus 1 to the nth. You expand this out. If I put a 1 here, I get the first term. Or for the 2 here, I get the second term. We're good there. I would just need to figure out what power the -1 would have to be raised to in order to alternate from positive to negative and then back to positive. So what I would say is, okay, try an n. If that doesn't work, add a 1 to it, right? Because if you think about the alternating series, in general, it was -1 to the nth, or -1 to the n plus 1, or -1 really to the n minus 1, but some deviation from -1 to the n, right? If I put a 1 in for n here, will this be a positive number or a negative number? -1 to the first power is what? -1, all right? Well, I want it to be +1, all right? So I need to guarantee that it'll be an even number, so I'll just tack a +1 on that. Now if I plug a 1 in for this, 1 plus 1 is 2. -1 to the second power is positive. When I get to the second term, it'll be odd, which will make it negative. When I plug in the 3, that'll make it even, back to positive. And so now I have a rule for the infinite expansion. All right, like I said, I'm stealing my own thunder a little bit because I have a whole lesson on just coming up with this stuff. All right, we're going to explore more of this, but really this is the ultimate goal, because if you think about what we were doing before, with all those different tests, especially the alternating series tests, like we're getting into the idea of being able to approximate a sum with a certain degree of accuracy. I can now, if I wanted to, start thinking about how many terms would I have to go out in order to be accurate to, let's say, 10 units on an XY plane. All right, so it's centered around 1. Maybe I want it to be as accurate as far as from a domain of 1 to 11. I could start thinking about how to make that happen. Maybe 1 to 20. Maybe I want it to be infinite. I don't know. All right, but we can start building our way towards understanding that stuff. But ultimately, the question ends, this particular question, the way it's phrased, and I want to make sure you understand this. This question stops here. All right? That's all it was asking you to do. This is me just foreshadowing what's to come. All right? So I'll even draw a little line there. Very important, because I don't want you thinking that you got to do all this stuff for every question on the test. If a question just said find the 60-degree Taylor polynomial, you're finished at this step, and that's the end of it. This is what's to come. All right, so with that, I'm going to put stars on the next two bad boys. It's weird because the second example, the third example, looks like it would be like the hardest one ever. It's actually the easiest one ever because they give you everything you need to know, right? But I'll let you play around with that. So let's take 5, and then we'll continue on after the break. So we need some derivatives. You're always going to need those. You don't actually have to always find them because sometimes you'll just have a good sense of what the derivatives would be. You know, exponential e is kind of nice. So we have f of x e to the x minus 5. If I take the derivative of that, it's going to be e to the x minus 5 times the derivative of the exponent, which is 1. So that my first derivative is going to be the same as the original function. Okay, so what that's telling me is that any derivative I take is still going to be the same thing as the original function, which is the best possible news. All right, now we're centering this around 5, so we're looking for f of 5. All right, and so 5 seems to be, you know, at first glance, some weird value that was selected. But when you go through the calculations, you see that it's the perfect value because you get e to the 0th, which gives a result of 1. In both cases. Oh, I wrote f of 5 a second time. Nth derivative at 5. That would be e to the 0th, which again is equal to 1. Right? So there is kind of a method to that. So if you're thinking in terms of transformed functions, you know, so the Maclaurin polynomial for y equals e to the x, it would be centered around x equals 0, right? Definition of a Maclaurin polynomial. In this case, a Taylor polynomial, you know, we still want to kind of manufacture that 0 result, right? The parent function, e to the x, the perfect value for x would be 0. E to the x minus 5, the perfect value would be 5 because that gives us a result of 0, right? So if you're still working on your tech assignment, that concept may come into play a little bit. All right. So we have derivatives. Now it's just up to the general structure of the thing. So we're looking for 4th degree polynomial. Right, so it's always, oh, it's actually not on this page. Okay. I was going to say, I'll just point to it because, like, I copied it out to this page, but I didn't. Well, I can at least point to this. So you have the f of whatever, in this case f of 5. That gives us our first term. But it's really that value multiplied by x minus a to the 0th power over 0 factorial, with all that other stuff canceling away. All right, so it's really, I don't want to say coincidental, but it's really not just a matter of saying, well, the first one is f of 5, and then after that we have a rule that we follow. It's the same rule all across the board. All right, so you could even write it out by saying that I'm looking for f of 5, undo. Jeez Louise. Off to a rockin' start here. So f of 5 over 0 factorial times x minus 5 to the 0th power. That's actually the first term. It's just all of that simplifies down to just a 1 because these cancel and f of 5 we already figured out is equal to 1. All right. and you don't have to write that, but I'm just doing this for instructional purposes. So the second term is the first derivative at 5 over 1 factorial x minus 5 to the first. All right, so that simplifies. Now, the derivative, any derivative at 5 is still going to be equal to 1. Right? So it doesn't really matter what, first, second, 10th derivative is still going to be 1. Right? So this is just going to clean up to just an x minus 5. So plus 1 over 1 factorial if you want, but really it's just x minus 5. The third term would be f double prime of 5 over 2 factorial times x minus 5 squared. So plus 1/2 x minus 5 squared. So that's what all this boils down to. Triple prime over 3 factorial x minus 5 cubed gives us 1/6 x minus 5 cubed. And we had to come out with a 4th degree polynomial, so the next one would be 4th derivative at 5 over 4 factorial x minus 5 to the 4th. So plus 1 over 24 x minus 5 to the 4th. All right, so all of that is our 4th degree polynomial. Yeah, and it's a lot, which is why, which is why we come up with the infinite series. I don't know if that's necessarily the case. It is simpler to write it as an infinite sum rather than writing out 4, 5, 10 terms of a series. I mean, that's troublesome because the more terms you include, the more you have to write. All of this stuff I included here, you wouldn't have to write any of that. You can go right to this line, but again, I was just showing for instructional purposes. And it's good to get at least a couple of problems in where you go the distance, just so you get a good feel for the actual Taylor polynomial. Right? Then after that, you start streamlining it. Otherwise, you're just following steps and you never really understand why you're doing what you're doing. All right, so the next one, suppose g is a function with continuous derivatives, and that g of 2 is equal to 3, g prime of 2 is equal to -4, double prime and triple prime are given. Write the Taylor polynomial of degree 3, 3 for g centered around 2. So that's good news. They did all the work for us. Well, at least all the derivative stuff. So p sub 3 of x would be equal to 3 plus, you're looking at -4. So I guess I could say minus. I'll just kind of cut the fluff there. Times x minus 2. Plus 7 over 2 factorial times x minus 2 squared minus 5 times x minus 5 over 3 factorial x minus 2 cubed. And I'm perfectly fine with you leaving it in factorial notation. So, I mean, over here I wrote it as 2, 6, and 24, but if you leave it as 2 factorial, 3 factorial, 4 factorial, whatever, that's fine. There's no real need to expand it out. Unless you're actually doing something with it, which I don't think you would be. All right, but you can see we're following the same process, except I'm not writing out all the notation.
And the 3 and the 4x, and the negative 4x minus 2, that is 0 factorial and 1 factorial.
Correct.
Writing it out.
Exactly. Third degree Maclaurin polynomial for e to the x. So we need some derivatives. Fortunately, it's e to the x, which has a derivative of e to the x, and a second derivative of e to the x, and a 20th derivative of e to the x, which is just wonderful news. All right. So since it's Maclaurin, I want to do it at 0. So f of 0 is going to be equal to 1. The nth derivative at 0, e to the 0th, also 1. All right. So this is where we start getting into the benefits of using Maclaurin and Taylor polynomials. You can see in part B that it's asking us to find a limit. Right? You could also be asked to find derivatives and antiderivatives, things like that, but more on that in a sec. So the third degree polynomial p of x, p sub 3 of x, 1 plus 1 over 1 factorial x, so just 1 plus x, plus 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed. All right. And you could leave it like that. I mean, there's no reason, there's no requirement to expand out the factorials. The only reason I did it with the natural log question was because in expanding out or simplifying the factorials, it helped me cancel a common factor, which actually helped me develop a rule a little bit easier. Right? So, but what we're doing here is we're using our answer to find a limit. Now, e to the x, if I were to plug that in for f of x, I get e to the x minus 1 over 2x, which is indeterminate. I would apply L'Hopital's rule, and after a step or two, I would get the answer. It's not that crazy. But if I use my approximation here as something that can replace f of x, looking at 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed minus 1 all over 2x, you can see that the 1 and negative 1 will cancel, and you're going to be left with x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed over 2x. Simplifies further, because we're still not out of the woods. If you were to replace all the x's with zeros, it would still be indeterminate. You could still apply L'Hopital's rule, but it's kind of defeating the purpose. Every term is divisible by x, so I'll divide an x out of everything. 1 plus 1 over 2 factorial x plus 1 over 3 factorial x squared over 2, and then when we apply the limit, lo and behold, we get 1/2, which is actually what you would have gotten if you applied L'Hopital's rule, replacing f of x with e to the x. Our first derivative would have been e to the x over 2. Apply the limit, you would have gotten 1/2. All right, so the one thing to keep in mind is that this is not an infinite expansion. So what we're looking at, and this is like it's the cool part, but it's also the part that allows it to work. Maclaurin polynomials are centered around 0, which means that it has its greatest degree of accuracy at 0. So at 0, it's a perfect match. If you're thinking in terms of correlation, like in a stat class, it's got that correlation coefficient, that R value of 1, that perfect fit at that value that it's centered around. All right, it's for each term after in the expansion, it allows it to be more accurate as it radiates away from that center. All right, but at that, you could even think of it as the epicenter. It's the most powerful, like an earthquake. All right, so looking at the limit, you can see we're looking for a limit as x approaches 0, which in a Maclaurin polynomial is perfect because, again, that's what it's centered around. If I were looking for the limit as x approached infinity in this case, this approximation would be terrible, right? Because it's most accurate at 0. This polynomial is going to be nowhere near as accurate for extreme values of x as it is at 0, all right? So if I'm at 20, 50, 100, 100 million, I'm going to lose accuracy. So whatever I come up with as a limit, it may not be even in the same stratosphere as the correct answer. But around the central value of 0, it's going to be very accurate, a perfect match. And since we're approaching 0, that's how you can justify using this approach. All right? So you think of it this way. If I asked you a limit question on the previous page where we did the natural log question, that was centered around 1. If I ask you for the limit as x approached 0, not a reasonable question because you're going to lose some accuracy. I mean, it could be reasonable if you're just looking for an approximate value, but in terms of getting a spot-on exact value, probably not the way to go. But if I ask you for a limit as x approached 1, now we're talking. All right, you'll get a really good, accurate answer in that case. All right, the same thing holds for derivatives and antiderivatives. So if I asked you for the area under the curve, all right, so consider this for a second. If I wanted the area under the curve, e to the x, going from 10 to 20, not a good idea. It's centered around 0, it's most accurate at 0. But if I wanted the area under the curve from -1 to 1, maybe not so bad. All right, I'm going to lose some accuracy, but if I'm just looking for an estimate, I'm going to be in the right neighborhood. If I go from -0.2 to 0.2, very accurate. All right, the closer I get to 0, the more accurate it's going to be. Now, if I want to go from, let's say, -10 to 10 and still use a polynomial, I need more terms. How many more terms? That's a different conversation for a different time. All right. So the next one, I think you're perfectly qualified to handle. Suppose the function is f of x is approximated near 0 by a third-degree Taylor polynomial. So given, we would want to find the value of f of 0, f prime of 0, f double prime of 0, f triple prime of 0. So this is actually having us work backwards. So if we know that f of 0 is going to be see if I want to do it as an intuitive approach or something else. No, I'll be a little bit more procedural about it. All right, so the first term. The first term of the Taylor polynomial is f of a over n factorial. 0 factorial, not the general term. All right, so in this case, we're doing it at 0, so it's fine. All right, so the first term, which is position, really the power of 0, would be this. All right, so in this case, what we're looking at is f of 0 over 0 factorial should give a result of 2. All right. Now simplify, clean it up. 0 factorial is equal to 1, so we arrive at very simply, f of 0 is equal to 2. And you might say, well, why'd you do all that work? I could have just looked here and said, well, it's 2. That's easy. But then you get to, well, not even the second term. The second term is still okay. We're looking at, I'll kind of cut to the chase a little bit. F prime of 0 over 1 factorial. And that should be equal to -5. Sorry, 0. Let me just rewrite it a little bit. It's kind of like synthetic division from back in the day. If there's a power not accounted for, there's an assumed coefficient of 0. So really this could be thought of as 2 plus 0x minus 5x squared plus 8x cubed. All right, so a little trick there. But still, once you get to that, it's the idea that, well, 1 factorial is 1, so f prime of 0 is going to be equal to 0. So I have that. The third term should be the result of f double prime of 0 over 2 factorial. So now this is where it starts changing up a little bit. That gives us a result of -5, because again, we're not worried about the powers, the variables and the powers. Right, those are accounted for. It's centered around 0, so it's a Maclaurin, and the powers, they're in ascending order, so there's nothing funky going on there. Right, but when you solve this for f double prime of 0, you get -10. And so the last part would be the fourth term. F triple prime of 0 over 3 factorial should equal 8. So f triple prime of 0, 3 factorial is 6, times 8 is 48. All right, so just pulling coefficients, I mean, assuming that you made this deduction first, you could just pull the coefficients for the first and second terms because the denominators are equal to 1. They're not impacted by the factorials. But once you get past the second term, the third, fourth, and so on, they will be impacted by your factorial denominator. So part B, does f have a local max, a local min, or neither at 0? All right, and so this is a little bit of a review of Calc 1, maybe late pre-calc, depending on how things work. So we have some calculus-related skills that, early calculus-related skills that could come into play. And so this, I think, is kind of a nice way to get across the importance of the Taylor and Maclaurin series, because what this is telling me is that if I can approximate a function f of x, you got to imagine that this is something that's not a polynomial function. Otherwise, why would we approximate it with a polynomial function? We would never approximate a polynomial with another polynomial. And in fact, if we tried to do that, make up a polynomial function, try to approximate it with a Taylor or Maclaurin series, you're going to get the same exact polynomial function, right? That's just how it is, right? So this would have to be something other than a polynomial function, right? Maybe something pretty complicated. Rational functions aren't terrible, but you get into trig functions, exponential functions, and things like that. Now, if you were to take the derivative of an exponential function or a trig function or something like that, you may come across an equation, a derivative equation, that when you go to try to find extrema, by setting that equation equal to 0, you stare at it for a good 45 minutes because you're like, I don't know how to solve this. But if you come up with the Taylor or Maclaurin approximate, now it's polynomial. All right, so a polynomial function, we can find derivatives of those very easily. And on top of that, we can solve them very easily. All right, once we take those derivatives. All right, so we're working off of the third degree Taylor polynomial. all this is asking us to do is take the derivative, so negative 10x plus 24x squared, all right, we're asked to determine specifically at 0 whether there's a local max or a min. All right, so that's nice. That means I don't actually have to solve this equation. You know, because when you're looking for extreme values, you take the derivative, you set it equal to 0. If it could be undefined, you set it equal to 1 over 0, and then solve. Here, that's extra work because they already gave me a potential solution, x equals 0. Right? So if you wanted to make a sign chart, you could, but all you would really need to do is find the derivative at 0. If the result is 0, that means that there's a critical value. All right, so that's telling me that the slope of the tangent line is equal to 0. At x equals 0. Therefore, it's a critical value. All right, slope of the tangent line is equal to 0 at x equals 0. Therefore, we know it's a critical value. All right. It may not be a turning point. It could be an inflection point. So what we do is we take that value and test it in the second derivative. The second derivative test for Extrema. So plug in the 0. Negative 10. All right, so my second derivative has a sign that's negative. Second derivative is negative at the critical value of x equals 0. So here's the $1 million question. Does anybody know what that tells us? You have a critical value, you plug it into the second derivative. If you have a negative second derivative, that tells us that the 0 represents a relative maximum. It's the opposite. Right? So if you were to get a positive sign, it would tell us that we had a relative min. If you had a negative sign, it means we have a relative max. And it's a logical way of kind of reasoning it out. If you have a negative sign, it means that you're concave down over that interval. If you have an extreme value over an interval in which you're concave down, it must be on the high side. Right? If it's concave up and you have an extreme value over that interval, it must be on the low side, right? Making it a relative min. Right? So therefore, we have a relative max, or a local max if you want. I mean, the question says local, so whatever. Relative and local are interchangeable at x equals 0. All right, so it's a little bit of a refresher of Calc 1, but you know, just imagine a question where you have a trig function, exponential function, some other kind of function, and you have to determine extrema. One thing that you might consider doing would be to come up with the Taylor polynomial or Maclaurin polynomial and then differentiate that and go through the process of making a determination of extrema for that particular value. So how do I know, because this is only a third degree polynomial, how do I know that what's good for this polynomial is going to be good for the original function? That's the big question, and it's a very important question. Does f have a local max min or neither at x equals 0? Specifically at x equals 0. Why x equals 0? Because that's what our polynomial is centered around. Suppose that the function f of x is approximated near x equals 0 by a third degree polynomial. All right. So we know that the Taylor and Maclaurin polynomials are stronger aka more accurate, depending on depending on how far away they are from the center value. All right. So if they're very close to the center value, then it's very strong. Perfect if it's at the center value. The further you get away, the more accuracy you're sacrificing. All right. So here, I mean, this is ideal because it's centered around 0 and we're asked to draw a conclusion around 0. Whatever's true for the polynomial at 0 is going to be true for the original function. Now, if I were to solve this equation by setting it equal to 0 and solving, I would get, let me see if I can do this real quick. 5/24, so, no, 5/12. So that's like close to a half. So like 0.8-ish, something like that. So it's not terribly far away from 0. So we will sacrifice a little bit of accuracy, but it won't be like drastically different. If one of the solutions was x equals -10, and the other was like +20, it's centered around 0 and it's only third degree, you could expect some significant variation. Right? But here, not so much. Same idea with the next page. Bless you. All right, the 8th degree Maclaurin polynomial. Now, that little chart a few pages down the line, that's your key to all this stuff. Because you don't have to figure this out. Yeah, it's 8th degree. Okay. That just means that my highest power has to be equal to 8. So look at the chart, a few pages down the line. It gives the expansion and then it gives the general rule. When you're coming up with a polynomial, you just don't need the general rule. All you need is the expansion. And you don't even need to go out too far. All right. The idea behind this is for exponential e, sine and cosine, you should never have to do any work other than just writing down the final answer. It's other types of functions where you should have to do some work. All right. So that's what's going on here. So in this case, we're looking at p sub 8 of x, 1 minus 1 over 2 factorial x to the second plus 1 over 4 factorial x to the fourth. I did not, it said Maclaurin. Okay, so we don't have to worry about what it's centered around because it's going to be centered around 0. 1 over 6 factorial x to the 6th plus 1 over 8 factorial x to the 8th. I left that space there in case you wanted to completely ignore everything I just said and do all the work. So shockingly, this is one of those situations where it's not a typo. There are some people that they look at it and say, well, better get to work. Derivative of cosine is, derivative of that is, plug in 0, and it's like, okay, yeah, go ahead and reinvent that wheel.
So if it was like either the x, we would just write the same thing.
Yeah, except it would be 1 plus 1. It's all positive, doesn't alternate. And then it accounts for every power. All right. Yeah, I've never been really big on mnemonic devices because this never comes out right. I've never really needed them. Like, to remember rules, I just remember them. But that's not to say that I just instantly have all the knowledge that I need. Like, I study them, and then when I commit them to memory, they're there for the rest of my life. All right? I do have a photographic memory, which tends to help. All right? But that's different. It's not necessarily what you would think. It's just like I have, like when I need to recall something, I recall the image in my brain of when I saw it in a textbook or online or something. Like I actually see the textbook page. Like that page I keep referring to you with the chart, like every time I say it, I'm seeing that image in my mind, right? So it's not like I know these rules, it's that I'm just accessing that image every single time I need to come up with the rule, which is fantastic for me, you know? Like, yeah, hey, just do that, you'll be fine. You know, so, but I don't have a mnemonic device to share with you. I do know, though, that between exponential e, sine, and cosine, you're looking at three very similar expansions. Each one has basically the same general structure. The sines are all the odd ones. The cosines are all the even ones. I just thought of it right now. Maybe a way to remember it would be that a sine function is an odd function. Cosine function is an even function. Honestly, I've been teaching for 20 years, this course at least for 10 to 12 years. I just now made that connection. Like, it is, of course it's the even polynomials because it's an even function. It's got to be symmetric over the y-axis. Otherwise, it wouldn't model the cosine function, right? So there you go. So you have the sine function is the odd function, which accounts for all the odd powers. The cosine is the even function, which accounts for all the even powers. They're alternating. Figure something out for that. I don't know. And then exponential e is positive, and it's everything. The way I remember that e is positive is just because I just think of an exponential e function. The entire graph is above the x-axis. So how that equates to pluses and minuses, I have no idea. I just know that the function is positive, so it kind of makes sense to me that the entire expansion would be positive too. All right, so, but exponential e has not just the odds, but also the evens all merged together. So same general structure, but it's got everything, but only positive. All right. Do you need to memorize that? No, but honestly, I wrote down this polynomial, like flash forward to tomorrow's test, I wrote down this polynomial before you would find the page that has that chart with all the rules on it, right? So the more familiar you become with these things, the easier it is to access that information. All right, so why do we do stuff like this? We talked about it on the previous page with the derivatives, but here we want to approximate the value of the antiderivative on the interval of 0 to 1 so that the error in your approximation is less than 1 in 500. Okay, so we'll deal with that in a sec. But so antiderivative on 0 to 1. Now we're using t here instead of x, but you know, we're anti-differentiating with respect to t. So it's this expansion. They said use your answer to part A, so this expansion just with t's instead of x's. Minus. Yeah, I almost didn't put the squared down. And also, just a side note, try not to forget that you have calculators. Oh, it's 1 minus this whole shebang, sorry. I'm like inspiring myself, getting distracted. Yeah, just because more often than not, when people get jammed up on this kind of stuff, it's not because they have no idea what to do. It's more so that they have the wrong idea of what to do. Like, you're supposed to approximate a cosine function, but you write the sine rule, or vice versa. So if you're in doubt, put the cosine function in your calculator, put what you think the expansion is in your calculator, and see if they generally look the same. All right? There are going to be some parts as it gets extreme where they don't match up, but around 0 they should match up precisely. All right. So all I did here was I replaced the cosine of t with its expansion. 1 minus, I just tucked that in at the end because I forgot to write it initially. But parentheses, hugely important because it's the entire polynomial that's being subtracted. So on 0 to 1, we're going to have the 1 minus 1, and then all the other signs are going to get reversed. And it would help if I actually reverse the signs. And that's all over t squared, which means that I can anti-differentiate once I divide out the t squared. Alright. It's kind of a pain to type this in the calculator, so I'm just going to do it by hand. So we're looking at 1 over 2 factorial times t minus, so we're just reverse the power rule. Increase your exponent by 1, divide by the new exponent. So 1 over 3 times 4 factorial t to the third. 5 times 6 factorial t to the fifth. And then 7 times 8 factorial t to the seventh. And that's happening over the interval of 0 to 1. Move that over a little bit.
Why does this happen?
Because they asked us. We have to find the antiderivative, so we increase the exponent by 1, divide by the new exponent. It's just instead of actually dividing this number by 3, for example, I'm writing it like this just for convenience. My voice cracked. That was weird. So I'm going to plug in the 1 because plugging in the 0 is going to be irrelevant. So we're looking at 1 over 2 factorial minus 1 over 3 times 4 factorial plus 1 over 5 times 6 factorial minus 1 over 7 times 8 factorial. All right. Now, so this is the part that's kind of weird. Well, I mean, the whole thing is kind of weird, but use your answer to approximate the value of rand. If you just left it at that, we'd be done. I mean, you could put it in your calculator, call it a day. It's that second piece there, so that the error in your approximation is less than 1 in 500. It's like, okay, so, like, what do you mean by that? Right, so it calls back to a piece of prior knowledge related to alternating series. And that's what we have here, positive, negative, and so on. I could continue the trend if I wanted to, because I have increasing factorials, they're all even, and then my multiplier seems to be the set of odd numbers, 1, 3, 5, 7. So the next one, if I wanted to, I could include a positive 1 over 9 times 10 factorial. And then keep going from there. It's just a question of whether I want to do that. Right? One of the things that we learned about with the alternating series is that you can approximate an alternating series by taking the sum of n terms, however many terms you want. The n plus first term would indicate the amount of error. Right? So what I would do here is actually figure out the very first instance in which I have a number that's less than 1 in 500. All right, so that's where the calculator comes into play. So, like for example, the 5 times 6 factorial. So 6 factorial is 120. So that's definitely less, because 5 times 120 is 600. All right, so this is valued at, and I'll actually just jot it down here, 1 over 600. Oh, this is a 72 hours. So 72, this is 1/2. And I might as well just do it all. Well, let me, oh, type that in wrong. No, it's still pretty huge. All right, so in this expansion here, what I'm looking at is each individual term representing the error of the sum preceding it. Right? So if I were to say, for example, and you could actually run the numbers in your calculator because, well, 0 to 1, the calculator might have a hard time with that just because of domain issues. But what this is telling me is if I only went out one term, I could say that that interval has an area of 1/2, give or take 1 over 72.
How are you getting like 4 factorial and all that?
So here,
No.
here.
Like, how are you getting 3 times 4 factorial for the first one? 5 times 6 factorial?
Like, are you asking how I got from here to here?
Yeah.
Yeah, okay, yeah, that's what I thought. So I'm increasing the exponent by 1, so that makes that the power of 3, but then I have to divide by the new exponent,
Oh.
which is the same as multiplying by 1/3.
Alright, thanks.
Shouldn't that be like 1 over, like, if I was on 600? Or am I doing it wrong?
Possibly. Were you talking about the very last one?
No,
This one?
yeah.
Maybe a different one. Oh yeah, 3,600. Oh, dang it, it was right on my screen too. I just didn't write the 3. Oh yeah, yeah. Anyway, so if I were to stop after the first term, I'm saying that I have an approximate value of 1/2, give or take 1/72 or 1 over 72. The decimal approximation of that would be my error, right? If I wanted to go out 2 units or 2 terms, I would subtract these 2, so I get this sum, with 1 in 3,600 being the amount of error. If I wanted to go 3 terms, then the 1 in 282,240 would be the amount of error, right? So what I'm just looking for in my alternating series expansion is for the amount of error to be less than 1 in 500. The very first time that that happens is here. So this is the error less than 1 in 500. All right, so my approximation would be 1/2 minus 1 over 72. In fraction form, that's 35 over 72. Which is approximately 0.486. So I'm just going to run a math 9 on this, on the original function, and I'll just pull up what the calculator, or jot down what the calculator says. So that's going to give us approximately 0.48638536762. All right, so the amount of error in the approximation. Now, we wanted it to be less than 1 in 500. So let's see if that ended up being the case. All right, so the error would be equal to the 0.48638537762, and from that I would subtract the 3570 seconds. I believe that was the number. Yeah. And so we're getting approximately negative, well, we don't need the negative because it would be absolute. So we're looking at an error of about 2.743 times 10 to the negative fourth power. Now if I compare that to 1 in 500, it definitely is less, which is less than oh, looks like we got it done.